All right, we're going to get ready for our next talk before lunch, so please welcome Muriel to tell you all about high-performance memory for the world computer. Give her a big round of applause.
Thank you very much. Hi, everyone. I'm Muriel Médard for the locals, and I'm co-founder and CEO of Optimum. Today, I'm going to talk to you about high-performance memory for the world computer. We just heard a bit about the importance of being able to access memory and access information. So I think that this is basically in the same line. So I have made the jump from academia into this wonderful industry, and this is really a tech transfer from my group at MIT. There, I held the NEC chair in software science and engineering for the entire School of Engineering, and been leading for over 20 years the network coding and reliable communications group. I'm an information theorist by trade, like many academic founders in this field. And I'd love to tell you now more about what we do and how we do it and why we do it. Okay, maybe just first a shout out to our backers. We have been very fortunate to have an amazing set of backers for our seed fund. We had an announcement about that not too long ago, led by 1KX. And so, why did we get all these wonderful partners? Well, because we're looking at something which is effectively necessary for any sort of computation, often taken for granted, but is actually becoming increasingly critical. And what do we mean by memory? By memory, what we mean is all sorts of propagation and access of memory. So think of uh, ephemeral memory, like the bus in a computer, and gossip in something like, for instance, Ethereum. Think of the read-only memory that you would have in your computer. So you write to it, but you don't modify it, you just read it, which is basically the ledger. Along with, of course, the proto-read aspect, which is data availability, is basically not actually doing a full read, just checking that you could do a read. That's our next step, Optimum DROM. And finally is the current state. And the current state in your computer, that's the RAM. That's the random access memory where you can check what's going on, read it, and then modify it, write it. That's the last step, the Optimum DRAM. So these are effectively growing levels, if you will, of sophistication in managing the memory. Okay, and why did I say that the memory is such a crucial part of any sort of computation? Well, I'll start at the middle. And this is basically what's often referred to as the von Neumann or the Princeton architecture, really sort of codified at the end of World War II when people really thought, okay, we've had to build computers. What are they? Well, this is what they are. They're machines. They take an input, they do something, and they produce an output, having done what they were supposed to do. And we think of the computer, of course, almost by its very name, as just computing. But in order to compute, one of the things that von Neumann knew deeply is you also need to have memory. You cannot compute without memory. You cannot compute on nothing, right? And in order to do that, you need to have a memory unit, and that memory unit needs to be able to be accessed both for reading and writing. So if we map that, say, to the Web3 stack, if you like to think of it as the world computer, what do you have? You have the stuff up top, the green stuff, application, execution, settlement, consensus, say, for instance, an EVM, and then all the applications running on effectively these operating systems. And at the bottom, you have the networking, state data, transaction data. Okay, so if we look at the top, the mapping, and if you've ever taken a class in computer systems or just learned it by yourself, you can pretty much recognize what's going on right now in Web3 and what's happening in a classical setting of a computer architecture as being very, very connected. Um, if instead you look at what's happening towards the bottom there in the memory unit, it looks very ad hoc, right? Like your computer doesn't have a gossip. It has a bus. That's how it actually transmits and propagates information, for instance. And of course, the memory is managed in a completely centralized way. Okay, so you could say, all right, Muriel, I get it. It doesn't look like what I did in class. So what? Why do I care? Since when do I care that it doesn't look like what I did in class? Well, if everything was going fine, we wouldn't. But what we know is that we have slow transactions because of low bandwidth, we're having massive storage costs, and we're having trouble scaling. And of course, as you look at things such as increasing blob size and the challenges that come with that, these sorts of scaling challenges are scaling in terms of size of transactions, in terms of number of transactions, in terms of number of nodes. These are scaling challenges across all dimensions. All right, so our products basically map to that taxonomy I gave you of what memory is. We start with Optimum P2P, and I'll show you more about it today, and particularly, show you some results from a testnet, with really just increasing bandwidth and reducing latency. That's it. It's a very, very direct value proposition. Then move on to the DROM, and then move on to the DRAM. And the way we do this, remember I mentioned that this is tech transfer from my lab. What have I been working on for my entire career? It's a technology which I'm going to tell you a little bit about, which is random linear network coding that I co-invented and came from my lab. Okay. You're using coding, that's great, but so what? What does it do? Let me start by showing you some performance benchmarks because, effectively, the proof is in the pudding. This comes from our testnet, and I'll tell you later a little bit about our fantastic testnet partners. So what you see here on the x-axis is the message size. So basically think of larger messages as basically the current evolution, particularly in Ethereum. And on the y-axis, what you see is the average latency in milliseconds. Now, what you'd like to have is you'd like to have the average, of course, be as small as possible. You'd also like the variability, which is the variance or the square root of the variance, the standard deviation, also to be as small as possible because you want the traffic basically to have low delay and also reliable delay. So what we see is a huge gain in the difference between Optimum P2P here, which is in blue, and Gossip Sub, which is in orange, both in terms of the latency average and the latency standard deviation. Now, one of the things I'd like to point out is that you see a really nonlinear behavior here, right? You see a behavior where it's not proportional to the message size. And you may wonder, why is that? Why, if I send you twice as much, then why isn't it just 2 times as slow? The reason for that is that there is a nonlinear behavior between delay and latency and total offered load. So as I increase my message size, I'm increasing my offered load. I could be increasing it not by changing my message size, but by increasing the number of requests, right? So if I simply increase the amount of traffic that's going through the system, that will also create that sort of increase. So this is very nonlinear. This is something that's known if you do queuing or if you do any sort of network analysis. And so it makes for a very, very steep problem with respect to basically overloading the system. This is exactly what we see on a day-to-day basis. You are basically in traffic. There's no traffic jam. You feel everything's fine. And then you have that very narrow window where there's no traffic jam, but you're still going at the speed you want, and you know that the traffic jam is coming, right? You know that it's coming. And that's exactly what's happening there as that orange goes up. So basically what we do is we improve all the time, but we particularly improve when the system is extremely challenged. So you know those horrible gas fee spikes, that's when the system's very challenged. And so you'd like to see an improvement at all times, and particularly when things are very bad. I told you that I would tell you a little bit about how we do this, so let me get into that. So what is RLNC, random linear network coding? It's a way of doing combinations of any sort of data shard. And these data shards, basically, one of the things that's interesting about them and what we're using here is that they're not just items, atomic items that you carry around like they were apples or oranges. They're numbers. They're living numbers that live in a representation, an algebraic representation, which you get to pick. And what we're doing in coding is we're creating equations in a particular way, which allows it to be entirely decentralized. So, here we are in France. If you think it really, most people assign, and I'm with them, sort of the creation of this sort of mathematics with Évariste Galois, a local boy. And he was a boy. He died very, very young, unfortunately. We can see that you can choose a representation to make equations in such a way that those equations are actually giving you the solution when you get enough equations to recover the original data. So here I have 5 unknowns. If you give me 5 equations, unless those equations happen to not be independent, then I can recover the original data. Now, the thing that's unique about our code is that you can create equations from equations. So I can be a node in the network that is not actually having access to the original data, but I can recreate an equation, which is a new equation, which didn't come from before. I don't need to just forward on the equations that already existed. So this is very different from traditional codes you may have heard of, like Reed-Solomon codes that are often used in data availability sampling, or in things like Solana Turbine, or codes like fountain codes, for instance, used in RaptorCast and Monad. These codes can be composed. So what that means is that you don't have a single entity that's creating the code forever and keeping it entirely fixed. You have a completely dynamic ad hoc code that is effectively composable forever. Okay. So, all right, you have a good code. That's nice. Then what? Well, what happens here is now anybody can benefit from having this much faster propagation, right? Everybody can benefit from the fact that you have much higher bandwidth, that you have much lower latency. Remember that, the bandwidth and the latency are basically just duals of each other, right? I can keep the same amount of traffic going and just have it more delayed, or I can try to lower the amount of traffic and have it less delayed. And you can see that here very clearly, right? If I was worried about traffic, say, on the orange and Gossip sub, I could, instead reduce my traffic by going to the left. So, for instance, when people talk about doing congestion control and say, oh, that's okay, I've got it. I've got congestion control. What congestion control is actually lowering the throughput. So it's managing your delay by lowering the throughput, which of course you can do, but yeah, you paid something for it. You paid for it in lower delay. If you really want to get the lowest delay, you just get your throughput to 0. Okay, so basically you have that trade-off right now, and what we're doing here is changing, completely changing, if you will, where those trade-off points are. If you kept going, of course, to larger and larger message sizes, eventually, yeah, or more and more traffic, you know, every system will reach a stranglehold. But we massively, massively modify where that point is happening. Okay, so everybody can benefit, whether this be, you know, L1s and L2s, whether these be validators, whether these be dApps, whether these be end users. Remember, I showed in particular the behavior that you see when you have a very congested network. That's really where end users will see that their system is not clogged up, that you're not going to end up, for instance, with horrible delays or really high gas fees. So everyone here benefits. Who's benefiting first? Well, validators. We went directly to validators. And the reason we've done this is because to some extent, they were the folks who immediately saw the benefit of this for their APY, right? I mean, the calls were just wonderful calls, super short. You know, you had all this really fancy, well, we had all this really fancy set of reasons why they should try us out. And within like 10 minutes, they're like, yeah, no, yeah, we don't want to see the rest of your presentation. We get it, just give it to us. So we've been very fortunate to work with this really fantastic group of validators. They've given us great feedback. They've tried it out. And if you want to get their own take on how well this works, I encourage you to look at our recent press release from last week, where we actually spoke about this, and the validators themselves went ahead and gave their own candid opinion of how this is working out. And of course, they've been very, very positive. So with that, would love to chat. In particular, if you're interested in items around delay, in items around throughput, in any of the things that we've talked about today, we would love to talk to you. Anything to do with memory, with propagation, that's what we do. And you know, I'll leave you with the following: that if you consider a computer, it's not the same people who build the operating system and the people who build the CPU and the people who build the memory. It's actually different teams of engineers. And therefore, I think it makes sense for there to be this mutual awareness and, of course, a lot of synergy, but to have a little bit more specialization. And this is our specialization. This is what we've been working on, and we're really excited to bring it to market. Thank you very much.